Hello everyone, welcome to my channel Physics for Engineers. I am Dr. Thirumal Rao Gurugubelli, Associate Professor and Head, Department of Basic Sciences, School of Sciences and Humanities, SR University, Warangal, Telangana, India. Today we will be discussing about the important properties of semiconductors. Let us discuss the most important characteristics that makes the semiconductors unique and highly useful in modern electronics. A semiconductor is a material whose electrical conductivity lies between that of a conductor and an insulator. The most common examples of semiconductors are silicon and germanium. One of the most remarkable property of semiconductors is their temperature dependent conductivity. Unlike metals, whose resistance increases with temperature, the semiconductors exhibits the opposite behavior. That means the electrical conductivity of semiconductors increases with increasing temperature. Whereas in conductors, the electrical conductivity decreases with increasing temperature. Or else in terms of resistance, we can say the electric resistance of conductors increases with increasing temperature. Whereas in semiconductors, it is quite reverse. The electric resistivity of the semiconductors decreases with increasing temperature. The semiconductors, as the temperature increases, the more electrons gain sufficient thermal energy to move from the valency band to conduction band. Consequently, the number of charge carriers increases in the semiconductors. That leads to higher the conductivity and lower the resistance. This behavior is known as negative temperature coefficient of resistance in semiconductors. To understand this better, think of a classroom. Suppose only few students are active during the class discussion. The communication is very limited. If more students are participating, the exchange of ideas became much more active. Similarly, when the temperature rises, more electrons participate in conduction. The electrical conductivity of the metals will be enhanced significantly. The another important property is that semiconductors behaves almost like insulators at absolute 0 Kelvin or minus 273 degrees. At this temperature, there is insufficient energy to excite the electrons from the valency band to conduction band. As the temperature increases, the electrons gained energy and became available for conduction. Perhaps the most significant feature of semiconductors is that their conductivity can be deliberately modified or controlled by introducing impurities. This process of introducing impurities into the semiconductor is called doping. The doping makes significant changes in the electronic band structure and electrical properties of the semiconductor. By carefully controlling doping, engineers can create devices with specific electrical characteristics, which finds many applications in modern electronics. This property forms the basis of transistors, integrated circuits known as ICs, LEDs, solar cells, and microprocessors. Today, the semiconductor industry, worth trillions of dollars globally, relies on these unique characteristics to manufacture billions of electronic devices annually. Therefore, understanding semiconductor properties is essential for every engineer working in electronics. Not only electronics, in communication devices, computer science, and material science, wherever you are working, the properties of semiconductors need to be understood properly to create, to innovate the novel materials for future applications. Let us discuss about the historical journey of semiconductors. Here you can see how the semiconductors evolved from the scientific curiosity to the foundation of modern technologies. The story begins in 1824 when Johns Jacob Berzelius isolated and identified the silicon. At that time, nobody imagined that silicon would be one day power the digital revolution. The next major milestone occurred in 1833 when Michael Faraday observed that certain materials showed changes in conductivity with temperature. So the temperature dependent conductivity was observed first by Michael Faraday in 1833, which behavior changed the shape of the semiconductor world completely, and nowadays the semiconductors are ruling the world in modern technologies. This was one of the most earliest observation of semiconductor behavior. Then almost after 40 years in 1873, William Smith discovered the photoconductivity. He found that the electrical conductivity of selenium increased when exposed to light. Means when the light is incident on the semiconducting material, The electrons on the surface of the material are interacting and responding to the light. This discovery laid the foundation of modern photodetectors, optical sensors, and solar cells. Just 1 year later, in 1874, Ferdinand Braun developed one of the first semiconductor device by observing rectification behavior in metal semiconductor contacts. Moving into the 20th century, scientists such as Arnold Sommerfeld and Felix Bloch contributed significantly to the theoretical understanding of electrical behavior in solids. How the electrons behaves in solid materials was explained by these two scientists. Their work led to the development of band theory of solids, which explains why materials behave as conductors, semiconductors, or insulators. The invention of the transistor is happened in 1947, marked a turning point in technology. After this innovation, the shape of the modern technology was significantly changed. Nowadays, every device, which may be a smartphone, computer processor, laptop, LED, any device, electronic device, which is made up of transistors and resistors. So these transistors are playing a crucial role in the modern technology. Before transistors, the electronic systems relied on bulky vacuum tubes that creates a lot of confusion in the device. So now the transistors made electronics smaller. Now we are using a smart devices, a portable devices after the invention of the transistors. Not only in size, which is faster and more reliable and energy efficient. Today, semiconductor technology powers smartphones, computers, artificial intelligence systems, internet infrastructure like broadband technology, medical devices, electronic vehicles, space technology. This timeline demonstrates an important lesson in science and engineering. Fundamental discoveries after take decades before transforming into the society. The semiconductor revolution we enjoy today in the result of nearly 2 centuries of scientific exploration and technology innovation. Having understood the development of semiconductor technology, Let us now look at the materials themselves. As the semiconductors can be broadly classified into two categories. One is elemental semiconductors. The second one is compound semiconductors. Elemental semiconductors are composed of a single element. The most common examples are silicon and germanium. These two, also known as intrinsic semiconductors, which are available in pure form. Among these, silicon dominates the semiconductor industry because of their availability in nature. More than 90% of electronic devices today use silicon-based technology. Why silicon? Why it grabs that much importance? Means silicon is abundant in nature, inexpensive, and chemically stable, and also capable of forming high quality silicon dioxide layers that are essential for integrated circuit fabrication. Coming to the germanium, it was widely used in early transistor because of its higher carrier mobility. However, silicon eventually became and preferred choice due to its superior thermal stability and manufacturing advantages. The second category is compound semiconductors. These are formally developed by combining two or more elements. Examples you can see gallium arsenic, gallium phosphide, aluminum arsenide, and indium phosphide, and there are many examples like aluminum phosphate and so on. It is not limited with these given examples. There are many semiconductors, oxide based semiconductors, chalcocite based semiconductors like ZNS, CDS, and oxide based semiconductors like TiO2, ZNO, SNO2. Like there are many compound semiconductors which exhibited the superior properties than the individual components. The coupled semiconductors are especially important in high-speed communication systems and optoelectronic devices. For example, if you take gallium arsenide semiconductor, which is used in satellite communication system and microwave circuits. Indium phosphate is used in fiber optic communication systems. Gallium phosphate is used in LEDs and display technologies. Each semiconductor material possesses unique electrical and optical properties, making it suitable for specific applications. As future engineers, understanding material selection is critical because the performance of the electronic device often depends heavily on the semiconductor materials used. Now let us focus on the important semiconductor, that is silicon. If you see the arrangement of atoms in silicon, you can see here how the electrons are revolving around the nucleus. And the right side, you can see the periodic arrangement of the outermost orbital electrons in the silicon crystal. You can see here in the outermost orbital there are 4 electrons. The 4 electrons will be make bonding with the 4 neighboring silicon electrons of the neighboring atom. Silicon belongs to group 4 of the periodic table and contains 4 valency electrons in its outermost orbital. These 4 valency electrons plays a crucial role in determining its electrical properties. In a silicon crystal, each silicon atom forms covalent bonds with 4 neighboring silicon atoms. This arrangement creates a highly stable crystal structure, and the covalent bond is formed when neighboring atoms share the electron. At room temperature, most electrons remains involved in these bonds, making pure silicon a relatively poor conductor. Because all the electrons are closely bound with the other electrons of the neighboring atoms. At room temperature or less than room temperature, the silicon exhibits the more stable behavior. However, the thermal energy can occasionally break some covalent bonds. When this happens, the electrons becomes free to move throughout the crystal. So when the semiconductor is subjected to the thermal treatment, some of the covalent bonds will break and the electrons become free. The absence of that electron creates a vacancy called a hole. Thus, two charge carriers are generated simultaneously. One is a free electron after breaking the covalence bond. The free electrons will create, and that vacant position will create a hole. Both contributes to the electrical conduction in semiconductors. This concept is extremely important because the semiconductor current flow involves two types of charge carriers. Unlike metallic conduction, where only electrons participate, the silicon crystal structure also provides a platform for doping. By introducing a small amount of impurity atoms into the silicon crystal lattice, we can dramatically alter its electrical conductivity. This capability enables the creation of N-type and P-type semiconductors. Then we can create diodes, transistors, integrated circuits. Every modern microprocessor contains billions of transistors fabricated on the silicon wafer. In fact, the entire digital age is built upon a simple yet elegant atomic arrangement of silicon. The next slide, we will see how adding specific impurities transforms the pure silicon into a different types of semiconductors and how it enables the practical electronic devices that we'll discuss in the next slide. Till now, we have discussed the semiconductors in general. Now, we classify the semiconductors into the two major groups called intrinsic and extrinsic semiconductors. You can see the classification here. An intrinsic semiconductor is a pure semiconductor without any uh, intentional impurities. As already I mentioned, the examples silicon and germanium, which are the examples of intrinsic semiconductors which are available in pure form. In intrinsic semiconductors, you can see the number of charge carriers. The number of free electrons is exactly equal to the number of holes. Therefore, we can say the number of electrons is equal to number of holes, which is equal to the number of charge carriers in the intrinsic semiconductors. Since the number of charge carriers are relatively small, the intrinsic semiconductors exhibit low electrical conductivity. To increase the conductivity, the engineers intentionally introduced impurities into the semiconductor crystal lattice. This process is called doping. The resulting materials is called an extrinsic semiconductors, are also known as doped semiconductors. The extrinsic semiconductors are further classified into two groups. One is N-type and P-type semiconductors. This classification mainly happened based on the characteristics of the doping element. Let us discuss about the N-type semiconductor. In N-type semiconductors, in N-type semiconductors, the pentavalent impurities such as phosphorus, arsenic, or antimony are added. In P-type semiconductors, the trivalent impurities such as aluminum, gallium, or indium are added. So these impurities dramatically increase the conductivity by increasing the number of charge carriers. Think of the intrinsic semiconductors as a small village road with limited traffic. Doping transforms it into a busy highway with significantly increased traffic flow. This simple concept forms the basic of all semiconductor devices, including diodes, transistors, integrated circuits, and microprocessors. In the flow of these charge carriers, increases the electrical conductivity, and that creates the opportunity to develop a new kind of electronic devices. So here I can conclude the classification of semiconductors. Thank you for your attention. Once again, I welcome you to my channel, Physics for Engineers. Thank you.